Hello, everybody. I'm Peng Zhao from the University of Tennessee, and today it's my great honor to introduce our speaker, Dr. Michael Gollner. Dr. Gollner is an associate professor and DAP faculty fellow in the Department of Mechanical Engineering at UC Berkeley. He was previously an associate professor of fire protection engineering at the University of Maryland from 2012 to 2019. He is broadly interested in fire science problems by utilizing experiments and combustion and fluid dynamic theory. Much of his work is focused on applications to wildfires, including their spread through vegetation, ignition of structures in a wildland-urban interface, transport of embers, fireworks, and emissions from wildfire smoke. Dr. Gollner has been active in professional society leadership, serving on boards for the IAFSS, WSSCI, IAWF, and NFPA FPRF. He has been awarded the NSF Career Award, Tsuji Early Career Award, and Prue Early Career Award in Fire Safety Science and Fire Protection Research Foundation Medal. He received his bachelor, master, and PhD in mechanical engineering from UC San Diego. And with that, I would like to welcome our speaker, and time is yours, Michael.
Thank you so much for the introduction, and thank you for inviting me here today. So I'm excited to talk about wildland fire in the context of combustion for our community. Before I get going, I want to give a thank you both to all the sponsors listed below. There's a variety of foundations, state and federal organizations that have enabled our research to happen. And first and foremost, the students and postdocs who have done really most of all the hands-on work. And so rather than listing them all in the beginning, I'm going to highlight them as we go through the talk. So the goal today is for me to review how combustion applies to wildland fire science. And I think there are so many opportunities. My take is probably different than someone else's, but I hope for the combustion community that this will be helpful to those that are interested in wildland fire, and we get more of our community involved in this problem through presentations and understanding of the problem. Before I delve in, I wanted to kind of throw back and talk a little bit about my own research, which is now at the Berkeley Fire Research Lab. As you heard, in 2020, we moved to UC Berkeley from the University of Maryland, and we tackle a wide variety of problems. Most of them are wildland fire focused. How do wildfires spread, fluid dynamics and heat transfer? How do fires ignite community? It's a lot of smoldering combustion, transport, ignition of solid fuels and porous fuels. Also a lot of modeling for wildland-urban interface, risk and spread modeling. As Professor Dreyer was mentioning, fire emissions. Fire emissions are huge, and we've done a lot of work moving from wildland fuels, where we looked at the effect of the fuel type and how it burns, and now moving to wildland-urban interface fuels, and how that presents a risk to wildland firefighters. Fire whirls are an extreme wildland fire phenomena. We do a lot of work on them, but we've generally had funding to actually use them for oil spill cleanup, which is a completely different problem I can't get into today with the time, but it's kind of fascinating, and it's amazing what swirl can do to combustion, and we love learning about that. And then spacecraft fire safety, which Berkeley, through the PI, Professor Fernandez-Peyo, and I'm co-PI on several projects that are working on fire safety in space. Also something for another time. We're going to focus today on wildland fire. And before I begin, I think it's important we understand the context of fire. And I'm going to take a very US perspective. But you can see here on this graph, the number of fires in blue versus the area burned. And so we often hear there's more and more fires. Well, there's not. But what we are seeing is that the fires that tend to be devastating and tend to grow tend to be much larger and more devastating than they were before. They're on season, off season, regionally, but overall the trends of area burned is going up, whereas the trends of the number of fires is not. Now, if we backdated this, 100 years, we'd probably see something different because there was more acres burned, but it was burning differently. And we'll talk about that in a moment. And what does that cause? Well, we always focus so much on suppression, putting out the fire. And suppression is billions of dollars and doesn't really have the impact that we want. And so a lot of my research focuses on mitigation rather than suppression and active firefighting. We want to prevent the problem or reduce the problem before we get there. And I think I want to use California. I grew up in California and now I'm back in California because it's a very good visual representation of what we've done to change wildfire in the US and in many other parts of the world. On the left, you can see over 100 years of burned area. California is pockmarked with fires. It is a fire-adapted state, which means that the landscape and everything here is used to fire, has always had fire, and fire is just naturally part of the ecosystem. And so it burns a lot. And it used to burn at a certain intensity and certain times. Look at just a 10-year swath from 2011 to 2021. The same general areas are burning, but you can just visually immediately take that the average size of those fires is dramatically larger. And in fact, a lot of what's happening is that the fires are no longer burning as they used to in small fires and not the most extreme conditions. Now, they only tend to be getting out of control under the most extreme conditions. So what happens when that happens? We have losses. And so you can see some of those losses on the right. This is in terms of structures burned. I only have it up through 2020. We'll have to update. We're just starting to get more data. We have California data. We need to get nationally. You can see spikes. Northern California, the Camp Fire, the Cedar Fire. California is really sort of winning on a bad scale of structures lost to wildfire in the US and probably the world. But you can just see how this problem is sort of growing, and it grows in a spiky nature as there are devastating fires that go through traditional fire regions, but burn through communities. And unfortunately, it also results in loss of life. In Northern California fires in 2017, 22 deaths, and in 2018, the Camp Fire, 85 deaths. The other motivation, of course, is financial. Over $16 billion of losses in the Camp Fire. This is on the level and even above some hurricanes. And so now it becomes an even more pressing issue where insurance gets involved. And so unfortunately, these fires are getting worse. This is just a pie graph of structure destruction over time. And you can see between 1930s to 2000, 2010, 2020, the proportion of structures burning is growing over time. And the size of fires, which we call mega fires on the bottom right, are growing. So large fires over 100,000 acres per year have traditionally happened in the past, but not very often. Now they've become the norm. And there are some reasons for this. I call this the drivers of change, and people reduce this in different ways, but the way I best like to explain it is there's three main drivers, not for wildfire, but why wildfires are getting more extreme. The first is climate change. Depending on where you are in the US, climate may change differently, but it tends to produce more extremes with more drought, more extreme fire weather. And there can also be fuel die-out because of this. Long-term drought induces pine beetle outbreaks in the Sierra forests in California. Those dead trees fuel the fires. After those trees burn out, we may actually have a reduced fire load. But unfortunately, that may forever change the fire regimes and forever change the natural ecosystem here, which we don't want either. And so there are some really interesting long-term effects on that side that affect our fire behavior. There's also fire exclusion. We haven't let fires burn. Starting in the early 1900s, with Pinochet and other groups in the Forest Service, we wanted to put out every fire. And eventually we had the 10 a.m. policy to put out every fire before 10 a.m. on Forest Service land. Unfortunately, this means the fuel grows and grows and grows. And so we removed indigenous fire, which used to burn naturally. We prevented all fires on low fire danger days, and now only the very worst burn. And so this adds lots and lots of fuel to the fire. Finally, we're living in areas that traditionally burned. Areas here in Northern California have always burned. This hasn't changed. We're just not letting them burn on low extreme day, on lower fire weather days, and only letting them burn on extreme days. And we're now putting huge subdivisions right in their way. And so if we don't build with mitigation in mind, we're creating more and more vulnerable structures, and things like our power lines are causing increased ignition sources. So you can visually see this fire exclusion, the second point I mentioned. This is from Bob Keene. This is Douglas fir at about 4,400 feet. And you can just see from the 1900s, it almost looks prairie-like between the Douglas fir. But by the 80s, the forest is chock full of young, immature trees. And this creates what we call ladder fuels, which would just love to go from the ground all the way up to the top if we had a fire. And so if there is a fire, and I'm sure there will be in this area, it's going to have devastating consequences unless we do something to clear the fuel. Because the fire used to just clear the ground, not destroy the taller, larger trees, and maintain forest health. So where does combustion play a role in this problem? I think we have to back up before we even start the discussion and remember wildfire is a natural ecological process, and we've disrupted. So if anyone's been a proposal reviewer in many different federal agencies, you'll see all this fighting fire, stopping fire, stop all fires, put out all fires. Oftentimes, there's a bad premise to begin with, right? We have to remember, what's our role? Well, fire was already here. We want to prevent or stop destructive fire, right? There can be good and bad fire, and it's kind of hard to separate sometimes. But overall, our goal is not to remove fire, but to reduce risk. And so on the ecology end, there's a lot of people that look at benefits of this fire, downsides of that fire. Should we let this burn? Should we let that not? But on our end, if the fire gets to communities and to people, pretty much all the time, we never want our communities to burn, right? And so we want to design for that and have active forces as well to make sure that you prevent any kind of disaster. Now, as engineers and scientists, but engineers especially, we understand processes and then develop solutions. And so I think most of us in the combustion community do come from that engineering side, and we play an important role linking these ecological processes to the physical processes to actual solutions on the ground. So let me talk about some of those physical processes and where I think we have roles. So today I'll talk about fire behavior modeling. How do we actually model that fire moving? There's physical wildland fire science. What is the heat transfer? What's the pyrolysis, the fluid dynamics of combustion? What's the heat release? How does it actually play a role to spread? And then we want to model that process. Do we do it at a landscape scale in 2D? Do we use cellular autonoma? Do we completely AI and forget the physics? Do we do CFD and couple our models? There's all sorts of approaches. Wildland urban interface is where those wildland fire approaches meet the traditional sort of structure fire community that's been developed for the last 50 years. So how do we look at a fire moving through vegetation attacking our communities? We've always looked at fire on the inside. Now we have to look at fire on the outside, and then hopscotching from structure to structure. Fire emissions are also incredibly important, and I think have been very neglected from the community. So we look at emissions from engines all the time, but a big CO2 contributor is also from fire. What's the difference between a prescribed fire burning and an extreme fire that's uncontrolled? Oftentimes, prescribed fire releases a lot less CO2 and is better. What about our structures? What kinds of noxious effluents are coming out of there? There's a lot of open questions. And then the kind of, in a fun, in a destructive way, in essence, extreme fires. So things like fire whirls, eruptive fire behavior. There's a lot of these extreme cases that often capture our attention. They're probably not the most common, but they still occur, and it's interesting and important for us to understand where they occur and make sure people are out of harm's way and prevent them from time to time from occurring. So I'm going to start with fire behavior modeling. Is probably the area that combustion has played the biggest role over the years. We're talking about understanding the physical processes and modeling things like rate of spread and fire intensity. And for fire intensity, that's the term we use for heat release in wildland fire. So this is a video released from the U.S. Forest Service of a fire burning in Utah. It's the FASME, the Fire and Smoke Model Evaluation Experiment. I was not a part of it, but let's look at a fire process through tall pine. At first, you can see, if you can make out, there's already some little embers dropping, smoldering particles that may ignite fires ahead. At first, they're smoldering, and they come in greater and greater intensity, and eventually you'll see some of them may even be flaming. It all depends on wind speed and direction, but there's definitely smoldering particles flying all around. So we speed up a little bit. They're starting to smoke a little bit. They're starting to smolder more. And now some of them are flaming or already have enough energy to ignite spot fires, which drive the fire ahead of the front. But in this case, I'm not sure that those spot fires will actually dominate. You have such a tall and large, we call this a crown fire, moving through the top of the tree crowns. It looks like we even have some pyrolysis and vaporization ahead of the fire front, igniting the ground and some of the trees. And you can see that the treetops are igniting first before the ground, which is indicative of a crown fire behavior. Another thing that's really interesting to look at is that the fluid dynamics here is really interesting. There are puffs and motions and moves. It is not steady and constant and blowing, but that fire is puffing and moving and blowing through. And modeling the pyrolysis and vaporization in this process would just be massive undertaking. And then you can see turbulent diffusion flames everywhere. So there's a lot of scales when we look at wildland fire. We start with the fire itself. Combustions occurring in sub-millimeter scales. The fire line over which the fire spreads, this fire line can be a kilometer wide. But the fire itself within the line, the flame is maybe on the order of several meters. And so the fire dynamics is happening between the millimeter to the meter scale, but it's being spread over a line. And we typically reduce it to a line because it kind of spreads as a front, just like a flame front. And we ignore the depth and thickness, even though that's there. And that fire line is spreading and propagating the fire. So there's a lot of scales. Do you focus on the landscape kilometer scale or the millimeter scale of the combustion if you're interested in emissions? And then we are affected by the weather. And we're greatly affected by the weather. Oftentimes in the models, we just say wind speed and direction, but the reality is we have an atmospheric boundary layer that has different effects at different heights. We have topography, which is going to go from the meters to the kilometer scale. And these can channel flows and change things. We also have to remember that we have fuels. We often model fuels as 30-meter cells with a mix of fuels, and we just say that's a heterogeneous mixture, give it these properties. But the reality is there's a canopy, and there's a base, and there are cells within there, and then there are twigs and branches and leaves. There's so many parts, and we know that the structure of the fuel will affect the fire dynamics. And then, of course, there's homes, and the same sort of scales occur within a wildland-urban interface community, though we also can't forget the effect of embers, those small particles which fly. And those may fly within the atmospheric boundary layer, but we're very interested where they land. And sometimes these can start new fires a kilometer away. That plays a huge role on fire dynamics. So modeling fire propagation, we use operationally to look at the potential fire spread, where will it go? We actually use it more for planning, for training, and research than actual operations. So it's used for operations, but that's only a small percentage of the use. We use it so much. We do risk assessment. Which area needs more resources? Which area should have a fire done now or should have mitigation done? And so it's used all over the place. Now we use Rothermel. This is from Dick Rothermel from the Forest Service in Missoula, Montana in the 70s. Came up with this empirical equation for fire spread. It's a correlation to observed phenomena. So it's been done in the wind tunnel and then verified at larger scales. Not necessarily because it's right, but because it's useful. So Mark Finney, a colleague I work with a lot, also at the Forest Service, and developed the main operational fire models we use today. It's like to say, you know, the fire is going to spread up faster, and the model shows it spreading up faster, and it's going to go slower here. And so it really follows the right trends. but whether those trends add up to the right numbers is really subjective and depends on the situation. And the equation itself is interesting. You have basically a fire intensity term and another, the state of this proportion of the heat release, I call it a reaction intensity, the proportion of the heat release that is actually moving forward to spread the fire. So in traditional flame spread, we're looking at the heat flux from the flame. We don't usually relate that directly to the heat release, but here that assumption is made. And the fit for it is all very empirical, but it sort of works because it's been done on slopes and with wind. And then the wind and slope are just empirical factors. Again, this phi fit to experimental behavior at sort of meter scale. And the denominator is the heat to ignition. So it's simply a function of a bulk density and some parameter to talk about the specific fuel and the sizes of the particles, like a surface area to volume ratio, and the heat required for ignition. And so you can add in there the water content for moisture. To me, this always reminds me of a B number or a Spalding mass transfer number for burning rate, not necessarily spread, but because it's correlated to phenomena, it works well in a lot of situations. But there are caveats. It's one-dimensional, it's totally steady, fuels must be uniform, and it must interact with the fuels linearly. That almost never directly happens unless you set it up to happen that way. So there are all sorts of other correlations to spread it elliptically, to make it speed up and slow down, where those are not even necessarily empirical, but just a lot of knobs that have been turned to make it work. So a simple question for us, and on the bottom right, I showed two images from Rothermel's original 1970s report, is what actually drives the fire. You can see in a no-wind fire, there's a lot of indraft, and they assume radiation is dominant. And the right-hand side, in a wind-driven fire, radiation convection play a role. Though it's interesting, in Rothermel's formula, you never actually pick which one actually plays a role. You just skip that part and just correlate everything. So there's never any actual calculation of heat transfer. It's just an assumed term that's fit to how fast it spreads. It'd be better to actually know what that number is. What is the actual heat that drives ignition? And that'll tell us how fires spread. And so in wildland fuels, we know that fine fuels drive wildland fire spread. You know this from your starting a fire. Your tinder, your paper, you need little small fuels to actually start the fire, your kindling, and then to get larger logs burning. And so it's usually these fuels which actually drive it. And if you were to take a really thin millimeter diameter fuel and a 7, 10, or 12 millimeter fuel and put them in front of a radiant panel, in this case, 41 kilowatts per meter squared, definitely can ignite wood, you'll see something interesting. The large stick will ignite after about 30 seconds. You can see it ignites around 380 C at typical ignition temperature for cellulosic fuels. The blue particle, the 1 millimeter fuel particle, doesn't ignite. It's got all that radiation, but look at the surface area to volume ratio. It's cooling a lot per its volume. And so just looking at its heat transfer coefficient, that 1 millimeter particle is so much more efficient in cooling that it never actually gets to ignition with radiation alone. It does heat to a steady state that's higher, but it doesn't actually ignite. And you can try this if you happen to have a radiant panel in your lab and safety, and you have some blades of grass, you can put it in front and it'll eventually wilt. And so long as it doesn't wilt onto the radiant heater, it usually won't ignite. So to test all of this and understand, the Forest Service started these series of experiments in their large 3 by 3 meter diameter wind tunnel and used these cardboard cut tines. And so these uniform tines are very small and for the first time provided uniform fuels for fire to spread through. And so this was very important because spreading pine needles down doesn't really replicate fire behavior. You don't have those thin fuels getting heated, and you also have non-uniformity, so you can't track what's happening. And the objective of these experiments was to understand what's actually heating and igniting and driving the fire spread process forward. Before I show the video of the results, I want to show some temperature traces that we're going to see. And so on the left-hand side, you can see radiation in red, and radiation certainly kicks up and eventually is probably going to ignite some of the fuels if they're large enough. But what's really interesting is in the black solid temperature versus the blue gas temperature. And so it's zoomed in on the bottom right, and you can actually see these pulsations of flame, of hot gases over time. And that slowly ticks up the stair step of the solid temperature. And what that tells us is we aren't yet at a radiative heat flux sufficient for ignition on its own. And so something's happening with the flame that's helping to drive ignition. This is a top-down view of fire spread during one of the experiments. The wind's blowing from bottom to top. And you can see some interesting wavy structures moving through. It's a little hard to make out, though, exactly what's happening. We look from the front. We've now generated something strange. You can almost see two very tall peaks and a low trough. And if you focus on the bottom there, you'll actually see that that trough is not steady, but is pulsating back and forth, moving the fire back and forth forward out to the fuels ahead. And if we zoom in with a high-speed camera, we can see this almost ocean wave performance of the fire. And it's triggered by that match igniting, by the way. It's not actual ignition of the tines, but this is showing the motion of the flames, which are essentially moving, and the hot gases are also moving ahead of it. And so there are two things we observe. One, the motion is not steady. Two, the flames are being pushed forward, and in particular, they're being pushed forward in these trough regions. And so the structures that we see have been observed in many scales, from very small scale, these sort of streaks, which move through the flow. And on the right-hand side, these flame towers. And we've seen these towers, you can see in, maybe 12 across in that wind tunnel, the two that we saw in the video. We can see them far across in field experiments through grass, in wooden crib experiments outside, as well as in ground fires. Even in numerical simulations, where we use atmospheric boundary layer models to model fire spread with about 1 meter resolution. And so this is given a different picture of flame structure. We know the boundary layer is coming in and pushing the flame, but the flame has instabilities that are naturally going to form in a boundary layer. You have a buoyant instability, which is pushing it up, and you also have some shear-driven instabilities as the wind is pushing it forward. And in our case, we're forming these towers and troughs, and in the troughs, it's forcing the air down. And it forms these series of streamwise vortex pairs, which are essentially forcing downwards on the lower end and upwards in the towers. What this does is exactly what we were missing. It helps drive the hot gases forward through the fuel bed much further than previously thought and observed. What this means is that the image and idea of a tall flame standing there radiatively heating everything ahead isn't entirely accurate. There is a large proportion of convective and even, almost, it's still convective, but flame contact that's driving forward fire spread. The difference is it's not steady, but intermittent to unignited fuels. And so there are both these radiative and convective components. And on top of that, flame spread is now it's a dynamical system. There's a relationship between the heating and the forward motion. And we've modeled these instabilities at small scale to understand, and we see these troughs. We have a nice combustion of flame paper, actually have much more heating, even in the laminar small scale, because the flames and the hot gases are being pushed closer to the fuel surface. And at present in Missoula, Jason Forthover and Mark Finney and others have developed some models to help spread fires using this context. And so their work, and with Sarah McAllister, have understood more about the influence of gaps and ignition and can model individual fuel spread as we move forward. Now, in general, how far along are we in modeling fire spread? Well, this was just in 2003 by Terry Clark, who really made a lot of model progress in CFD modeling for fire, the coupled fire weather models. He said the science of wildfires is still in its infancy, and the physics of how they spread is still poorly understood. The development of numerical models that fully couple fires to the atmosphere is a necessary step toward better wildfire prediction. However, the models face the enormous task of treating a physical problem where the relevant spatial scales span 6 to 7 orders of magnitude. And also the problem of validation with observations. We truly lack good observation of fires. We usually have 2 pictures per day at 250-meter resolution. This is not enough to verify physics. And the few experiments where we have more data are often limited because of the placement of the sensors, the bandwidth, or other issues that limit our ability to get the science data we need. So fire modeling is still growing. What do we do now? Most of it's landscape scale fire modeling. Farsight and Flam Map are free, available for download from the Forest Service. They can do tens of kilometer simulations with 30-meter grid resolution, and you can download all of those 30-meter grid resolution, whether it's weather and fuels topography files from government resources. And they use this Huygens model and elliptical model. You only have a 1D spread, but you can turn it into an elliptical spread by using this model and a relationship between how wide and how long it should be, dependent on wind and slope. And so it's basically just a checkerboard landscape. It doesn't couple to atmospheric, and you can use it with level set, cellular automata approaches. I particularly like using it with risk-based methods because you can do many perturbations, but it doesn't pick up things like when the atmosphere and the fire couple together. For that, there's coupled atmospheric fire modeling, and it can be fully coupled where all the cells are talking to each other and things are more physics-based like fire tech, or it can be more empirical on the ground like WRF and S-Fire, or somewhere in between like FDS, WFDS, where you can select between these. And these operate at different resolutions. They're now working on quickfire, which is, again, a coupled atmospheric model, but is supposed to run much faster. I think in general, we need all these different types of models. We're going to need very physics-based models for validation and for research, but for live fire exercises, we're probably going to do things that are much quicker and much necessarily not as accurate, but are going to be able to pummel through many problems and give us these risk-based approaches. And so we need more of these tools in our tool set and more development of the submodels, such as embers that go into them. The treatment of embers and all of them is completely different. And many of them, in fact, are quite poor, and there's absolutely no field validation data. Now, data-driven modeling, there is a lot of opportunity. A lot of our parameters are very empirical or not empirical at all and total guesses. But I always caution, we shouldn't be replacing fire physics, but maybe use data assimilation, real data on the field, model parameter finding. Maybe what we use for embers is not accurate from a lab, and using real data can drive those constant parameters. But moving completely away from fire physics is always a bit of a fear, because we move beyond where the data is. So further challenges, coupled effects. The model adds slope and wind. What happens when you have slope and wind? We don't know. This is an experiment at the Forest Service. We've done it in our lab as well. My student ran a lot of those experiments, and it's very interesting how wind and slope interact together on a fire. Using a gas burner, we can control it and actually look at some of those effects. There's also a lot of fine fuel effects. We don't understand live fuels. Sarah McAllister has done a lot of work, you can see on the bottom right, where she's burning different live fuels and trying to understand the effect of moisture and oils and other content in those fuels. And there are solid phase processes that we also do a pretty poor job of modeling and understanding, like the smoldering front behind a spreading fire front. We also don't have a lot of validation. The satellites, like I said, don't update many times per day. The fuels are complex and changing. The weather is impossibly complex and coupled. And so we have lots of small scale, mid scale, and even large scale needs for more data. Okay, something froze. Can you see the screen? I think we've recovered. Okay, so I want to jump now to another topic, which is incredibly important, after we move through the wildland, what if it gets to our community? Why are our communities burning? We probably don't remember 20 years ago hearing about all these communities burning down. But now, whether you're in Gatlinburg, Tennessee, whether you're in from the Marshall Fire in Colorado, or Boulder, or you're in Paradise, California, Santa Rosa, California, there's so many communities which have been just devastated by wildfires. This in Santa Rosa was a suburban community. No one would have picked up wildfire risk here, at least traditionally. How did this happen? So fires in the wildland-urban interface context spread by somewhat different means. Still the same physics, radiation, convection, conduction, but what drives it we think of differently. We used to always think of radiation 30 years ago. It was thought to be responsible for ignition, and you move the fuels away from the house and you're going to prevent it from igniting. But it turns out that didn't always work. We have these defensible space zones, like I said, moving the fuels away, and that really does help. But homes are still igniting. Another is direct flame contact. Even if you move the bulk of the fuels away, there can be small fires or a wooden fence. A fence that's wood is a totally flammable material. If you put mulch around your house, whether the fire spreads along some grass to the mulch, or whether an ember lands in the mulch, which then creates a large enough fire to break your window, either way, direct flame contact from nearby fuels can cause a fire. But what's most responsible? Embers. So embers or firebrands are small burning particles which fly through the air after breaking off of branches or other structures and eventually ignite. They're really difficult because they're flying Lagrangian particles while at the same time they're smoldering, and they're smoldering in flight, and then by the time they land, they sometimes accumulate, ignite other fuels, and will transition to flaming. So lots of coupled effects, lots of probabilities here, and it's those 1 in a million chances that tend to change the behavior. Unfortunately, look at a drive through a fire. This is from the UC Davis Fire Department at the Tamarack Fire. Those are millions of particles. So the 1 in a million chance is happening all the time because winds are so fierce in these fires, they're breaking off millions of particles. So most homes at the wildland-urban interface ignite due to these small embers, not the main fire front. You can see examples in the top left and bottom right, where roofs and structures have ignited without surrounding fuels. That happens because embers land on top and ignite inside and then burn out. You can see on the left, that structure was well protected on the outside, but must have had an opening through a chimney or a vent, and it burned it out from the inside. So how does this go from a fire to a disaster? We have to start with severe conditions, high winds and dry fuels, and that creates our extreme fire behavior. Large flame lengths, large heat release that's spreading rapidly. So that's just kind of a given. Then our homes ignite. But what is a difference between a disaster and just some fire is the number of homes igniting. So many that our resources become overwhelmed. If 3 homes ignite, you can get 3 trucks to handle them. If 300 homes ignite, no community has 300 fire engine crews on the ready. It's impossible to get to that point. Yet with embers, it's very easy for that many structures to be exposed at the same time. And that creates a disaster with hundreds or thousands of homes destroyed. So on an engineering perspective, how do we break that cycle? At any point, how do we break it? Well, we can reduce exposure. So what if, let's change the weather. No, can't do that. Well, we can move the community. We can design the community better. We can separate the community from the flammable sources. Embers will still come in, but less of them. We make a risk reduction. What if we do prescribed burning or fuel reduction? What if we don't have tall crown fuels? What if we, enhance the spacing so the fire coming nearby for the half mile around won't be as devastating? That can make a big difference. At the same time, let's harden the structures. Structures in California are all built out of wood. I'm not saying everything should be steel and concrete, but if you imagine the outside of a structure as a protective shell, vents enclosing eaves, non-flammable roofs, decks not really touching, or non-flammable and altogether. Nothing flammable within 5 feet. All of these things contribute to making the home less and less ignitable. And if all the homes in a community are less ignitable, you really reduce risk. But there's so much engineering. We need the materials. We need to understand the fire spread. How many embers could ignite something? So how much protection do we need? And then there's the non-combustion aspect that is still important. Our notification, response, evacuation, and communication still play an important role of reducing life losses. So how do we study this? Well, we've done a lot of partnerships with other groups. On the top right is IBHS. It's the Insurance Institute for Business and Home Safety in South Carolina. They've done some amazing work in wind tunnels by exposing whole homes. We don't understand all the physics on the process, but we can understand what areas are actually vulnerable and then try to work on them. Embers have to be generated. The bottom left here, there's firebrand formation and breakoff. Then they transport. And I would say the best work so far is on the transport. So Sanchez Tarifa did a lot of fundamental work. Frank Albini from the Forest Service had models based on plumes of how far they might go. But it doesn't just go one spot. It spreads through a whole area. And we need to move our models to do that with a more risk-informed approach. And then we have to understand, once they land, what are they going to do? Where will they ignite and not? So much of the ignition work prior to the last 5-6 years was on igniting porous fuels, pine needle bed cellulose with embers, not with igniting structural fuels. And what we find with structural fuels is that you need a lot of them. And if you look here, there can be a lot of embers piled up in a spot which contribute to ignition. We also can understand more about where they come from. I don't think we'll ever know all the embers as it starts, but we've been doing a lot more work on generation. This is a test that we participated in with IBHS, but we have another model here at Berkeley where we use a wind tunnel to generate embers. And something that's interesting is the embers actually come after the fire process. So those smoldering pieces and branches start to flake off and fly. This is a chaparral fuel. And you can see really the embers are generated after the burning process and the smoldering fuels fly away. And those later land and ignite other fuels. So we've done a number of studies. One is on ignition. So previous students like Raquel Hakes and Hamid Salasedi did a lot of studies looking at ignition of dense fuels. And we continue this work with colleagues in Maryland and other students here. Whether you have sticks or simulated fuels, an ignition from a single firebrand is very different than an entire mass of firebrands. And so that's something that we have seen. That single firebrand is only peaking, 4 kilowatts per meter squared, very small. But if you take a pile of the same embers, you can now get top heat fluxes of like 28 kilowatts per meter squared in a spot. And so it changes with time, but we see that looking at piles, and in particular, actually different geometries, plays an important role. And so just to understand, what does heating look like from embers? This is a smoldering pile of objects, porous fuel, on top of a solid object. Increase the wind speed, increase the heat flux. You get glowing combustion, greater oxidation, and more heat flux. But it also reduces the duration of burning because the fuel burns out faster. And so this is very hard to put together in a single test or a single thing, because as you change the amount of fuels, you change how they land, you change the wind speed, it changes the ignition properties. But this is something we look at, and you can measure it with heat flux gauges. You can also measure it using infrared and looking at temperature changes over different materials. We also looked at it in crevices. This is essentially your decking board. And it's kind of interesting, by changing the angle with the wind made a big difference, because you have the wind blowing through. So our current PhD student Bryce and previous student Julia worked on this. And you can see that the heat flux in a crevice peaks to 70 or 80 kilowatts per meter squared. This is just from some smoldering fuel inside. So if you have the wind speed in the right direction and the right geometry, there's a really dramatic increase in the amount of heating that you can have. And so what's the caveat here is to just understand that how the fuels come in and how you do this plays such a large role. So we haven't gotten to the point where we can couple the modeling of the smoldering and get heating out of it in different geometries. And someday, hopefully, that will help us better design our fuels and better design our protection features. If we want to actually model woolly fires, it's hard. There's so many components. We have wildland fire spread, we have firebrand generation, transport, ignition, and then it comes from wildland fuels to the urban to the wildland fuels, back and forth. The structures must ignite, it radiatively heats other structures, it burns for a long time. So at this point, we have a base model. So there are some empirical aspects and some physical aspects, but we've been working, Dewey Pernumo is one of the postdocs here, to try to model woolly fires. It's primarily supported by the Moore Foundation and NSF. And our challenge and hope is to get this model so that as a fire spreads to the wildland, it jumps straight into the woolly, not really, but in our model, to mimic real behavior. And then we can see what changes will prevent that from happening in the future. Now, I know I want more time to talk about this, but there isn't too much time in the presentation. Emissions are hugely important. As a fire spreads, it starts, there's a pre-ignition phase, flaming. But just look at this picture. So much of the emissions is coming behind in the smoldering front. And so it's not just the flames themselves, but it's actually the long post-combustion region where we have oxidation, solid oxidation, and with smoldering that are releasing tons of emissions into the atmosphere. This could be from wildland fuels. It can also be from structures. It's not just CO2 and CO and PM. All of those have their own contributions, but there is a litany of other gases that we're just starting to uncover. Most previous work has been done with aircraft or by pile burning. We've started to do more laboratory scale experiments because, the aircraft's great to get an actual field scale measurement, but it's hard to know what was actually burning. Those laboratory experiments that are larger, you can see in the top right, that's just a pile. So we're not controlling combustion. We've now used, it's not brand new, but it's based on an old German apparatus, but this linear tube heater, so we can control the oxygen, the flow, the fuel properties, the moisture properties, the heating properties, and we can get fully flaming, fully smoldering, and whatever mix, and measure emissions under different scenarios. And so doing that is the work of Priya, one of the PhD students here, looked at smoldering versus flaming emission factors. This is just showing the particulate matter, CO, CO2, NOx, and SO2. We also have FTIR with 26 other effluents, but there's a huge litany of effluents. And what's interesting here is that this is for live, wet, and dry. So depending on the state of the fuel, you get really different emissions. It's not just Douglas fir, it's how wet is it? Was it living before? Did it just get water added? It really makes a difference in the emissions. And we want to further understand that and where that comes from and how that has larger effects. And so we don't have much time, but this is important because everything we do, whether it's for health or for environment, is about tabulating the emissions from fires. So we take on the top right our emissions that are measured from a fire and overall get an emission factor, the mass of fuel burned on the bottom with the mass of the effluent formed on the top. And in fact, we use this today with satellite fire radiative energy readings, so how hot that pixel is, and how much we assume the biomass consumed, big ifs there, to get emissions. And so this is reliant on understanding the state of burning and then figuring out what the emissions are around the globe. And some of these correlations between, on the bottom, this is modified combustion efficiency, so CO2 over CO2 plus CO, it's approximate level of smoldering versus flaming, actually correlates fairly well to PM and CO and CO2. One of the things we actually see problems is with moist and wet fuels, we see a lot of issues with the correlations. And some of that is because of the transition between flaming and smoldering. And smoldering isn't really picked up much from the fire radiative energy readings from satellites. And so there's actually some broader issues of, are we actually capturing the real emissions from fires? And I think some of our work in the lab can help improve the way we do this in the future. there's still a lot missing. Flaming versus smoldering isn't included a lot. On the right-hand side, you can see just how different the particles formed from flaming and, flaming a little bit and then completely smoldering conditions. We don't understand everything about what's coming out. There are time-dependent behaviors in combustion. We're just simplifying it to a single emission factor. There are different fuels, they're live and dead, there's physical processes, and I think that the combustion community has the unique knowledge and skill set to help link emissions to these fuel properties and burning conditions. And I think that should be a long-term goal for us to work on this. It's everything from air quality to the combustion devices that we might use in cleaning up. This is even more challenging. Live fuels are changing, but I think we have the right skill set to contribute to this problem. And we have a lot of laboratory apparatus that we can modify to further understand. We just have to remember that we're dealing with living fuels, and we have to make sure that we compensate and we account for that when we know what we're burning. So I'm not going to have much time to show this because this has often been in the fire community, but there are lots of large fire effects. This is a review that Nai and Liu presented at the Combustion Symposium. So I'll just highlight it here that there are mass fires where large fires make a large area. Fire and weather interactions, fire whirls, eruptive fires, crown fires, and the spot fires, which we have discussed. They're all related to fluid thermal coupling, and they remain important issues for us to study. I'm just highlighting, I think, some of those that I think have some very big impacts in short time scales, whereas these are, we've understood some of the phenomena. There's a lot more to do, but I don't know if we have the biggest impact from this work as we do on some of the basic fire behavior and emissions and other topics. So in conclusion, I think that wildland fire science is ripe with interesting and impactful research challenges. We have many skills to contribute. We have the chemistry and chemical kinetics. We know how to couple thermal and fluid behavior. We have simulation expertise, and we have experience doing validation work, coupling that with experiments and modeling, but we have challenges. This range of scales of this problem is much greater than any engine or turbine combustor. We have poor input data, and we need to improve it. Solid phase kinetics sometimes is more important than gas phase kinetics. And solid phase kinetics happens in the combustion community, but not as much as gas phase. And so we have multi-phase stochastic processes, and we need to coordinate. A lot of times people want to focus, I'm going to solve the problem. Well, you can't just solve a problem with the physics alone. There's a lot to learn, but you need to work with people who actually work on the ground and in the field to make a difference. And those collaborations and that input makes a big difference so that what you're doing is actually realistic, like the real world. And just remember that fire is a natural and uncontrolled process. So we're never going to control all the input variables, but if we understand them better, we can mitigate our losses and hopefully improve the environment and people's lives surrounding these areas. So with that, I will conclude and play some fire videos for you and take questions.